All right, so we're excited to have Kefan Dong present. He's a first-year PhD student at computer science at Stanford University, advised by Tengyu. Before that, he studied computer science as part of the Yao class at Tsinghua. His research interests are in reinforcement learning and online learning. And today he's going to present some joint work with Tengyu and Jiaqi. You want to take it away?
Sure. Thanks for the nice introduction. So today I'm going to talk about our new paper, Provable model-based nonlinear bandit and reinforcement learning. So this is a joint work with Jiaqi from Tsinghua University and Professor Tengyu from Stanford. So in this paper, our main goal is to build a theory toward deep reinforcement learning. So first of all, the deep reinforcement learning theory is a big open problem because the existing reinforcement learning theory cannot apply to neural networks. Indeed, there is a very nice table from a recent paper by Du et al., and it summarizes many existing reinforcement learning settings with theoretical guarantees, but none of these algorithms or theories give polynomial sample complexities for even one-layer neural networks. Okay, before I jump into the hard instance, let me quickly introduce our problem setup. So in this talk, I'll focus on the neural net bandit, which is a simplification of deep reinforcement learning because there's no sequential aspect. And in this case, the reward function is denoted by eta of theta and a. And theta here is the model parameter, and a is a continuous action. Okay, as an example, so the linear bandit can be written in this form: the eta of theta and a equals the inner product of the model parameter and the continuous action. And of course, the neural net bandit, the reward function is given by a neural network that parameterized by theta, and the input of the neural net is the action. So in this talk, we work on the realizable and the deterministic reward setting. So in each round, the agent observes a ground truth reward, eta of theta star and a, after playing an action A. So the goal is to find the best action A star that maximizes the ground truth reward. Okay, and our first result is that a neural net bandit is statistically hard to learn. So actually the construction is quite simple. The model class and the action are all units L2 ball in d-dimensional space. And the reward function is given by the ReLU of inner product of theta and a minus some constant 0.9, for example. And you can see that the optimal action in this case is just the action that maximizes the inner product of theta star and a. So in this case, a star equals theta star exactly. So the figure below is the visualization of the reward function when the action dimension is 2. You can see that the floating disk is the reward function. And there is a peak in the rightmost part of this disk. This is because theta star here is pointing to the right. And the orange circle at the bottom of this figure is the boundary of the action set. So actually, you can see that there is a very large flat region in the reward function. And of course, there's a small region with non-zero reward. And this region has a exponentially small probability mass. So in this case, if we just take a polynomial number of actions with high probability, we're not going to see a non-zero reward. So all the observations are 0. So this means that finding the non-zero reward for this instance is like finding a needle in a haystack. So it requires exponential number of samples to find a non-zero reward. Okay, and also we can make this reward function smooth just by replacing the activation, by some smooth function. For example, the ReLU squared. You may ask that whether the hardness is because of the large flat region. And of course, if you are familiar with reinforcement learning language, this is the sparse reward problem. But the answer is no, because we can always add some gradient to the flat region. So here, the construction, we change the construction a little. So the reward function consists of two parts. It's a linear part plus a small nonlinear part. And the nonlinear part still has a exponentially small probability mass. Okay.
Kefan, can I ask a question?
Sure.
If I don't allow you bias, is it possible to construct hard instances? Because I feel like, coming from deep learning theory, I feel like when there's bias, we can't learn anything. When there's no bias terms, we have a lot of positive results in supervised learning.
Bias in the ReLU?
Like the ReLU, the intercept, the minus 0.9.
Do you mind just actually elaborating on why is the 0.9 usually a problem?
Sorry?
Basically, is the 0.9 usually a problem for exactly what this picture says?
I mean, in supervised learning, it's just, I don't really know why, but yeah, I think it's basically this. It's like I can make you just see always the response is 0. So you can do prediction, but you can't do parameter recovery. And that's basically what's happening here. In supervised learning, if you have biases, you can control prediction error, just no parameter recovery and no L infinity error.
Just jump in quick. So what if we incorporate the bias into the inputs, like add an extra dimension, like then everything looks homogeneous, but it is not actually, right?
You can get, I mean, you can put the bias into the X, but what happens? You can still only get prediction error. You can never learn the parameters. And basically here you want to find the argmax, which is like either L infinity error or parameter error, roughly speaking. So it feels like if you don't have the bias, it's probably learnable. I don't know, I'm just speculating.
Yeah, I guess if you allow me to constrain the action set, then we can move the bias term to the extra dimension of the action. But if we're not allowed to do that, I'm not sure. So yeah, maybe we can talk about this offline.
Yeah, sounds good.
By the way, some similar differences already apply to linear bandits, right? Like if you shift the unit ball, it's harder to learn than if you don't shift the unit ball.
Right. You are right. Cool.
So could I ask one more question? I'm
sure.
sorry to interrupt you so many times already. So I just wonder. So this bandit problem that you're showing here, this is essentially a convex bandit problem, right? So your reward function. I see. It's the reward function that is convex, right? I was going to ask about like the relation with bandit convex optimization, but here you actually have like a concave loss function, convex reward function, which is difficult to optimize, and maybe that's where. Yeah, I was just wondering, because there exist positive results for bandit convex optimization that show that, well, it is possible to get polynomial regret in the number of dimensions, but yeah, I can see now why this is a lot more complicated.
Yeah, this would be easy to minimize, but you can't maximize.
Right. Okay. Right, so let's continue with this construction. So in this modified construction, we have a linear part plus a exponentially small nonlinear part. So in this case, if you again, if you just take some random actions, probably you can learn the linear part easily. But there's no way that you can learn the nonlinear part because it has exponentially small probability mass. Okay, so this construction, although it's quite simple, but it has several implications. The first one is that with this construction, we show that a convergence to a global maximum is generally statistically intractable for neural net bandit. And also, existing reinforcement learning theory cannot apply to neural nets because they all aim for a global maximum, which is statistically intractable. Okay, so in order to fix this, we propose a new paradigm for bandit and reinforcement learning. So this is quite similar to that people use in supervised learning. So the paradigm consists of two parts. The first part is to show a convergence to a local maximum for general instances, which is the focus of this talk. And the second step is to show to analyze the landscape of the true reward in an instance-dependent manner. So perhaps for some instance, the true reward is concave, then we can converge to a global maximum. Okay, and our main result in this case is summarized by the following theorem. So under some literature assumptions on the reward function, there exists an algorithm that converges to an epsilon approximate local maxima in this R of theta times epsilon to the -8 steps. And R of theta here is a complexity measure. It measures the hardness of online learning with respect to the model class. I'll define this rigorously later. And we also have a similar result for nonlinear reinforcement learning. But the reinforcement learning result requires many, many more assumptions. It only works for stochastic policies. So because we are only, we're only looking for a local maximum, so one of the natural baseline is to use zero order optimization. So in zero order optimization language, we only care about the true reward, here denoted by f of a equals eta of theta star and a. And the zero order optimization algorithm estimates the gradient by some finite difference. So in particular, if we take a random direction, Xi, drawn from the unit Gaussian distribution, and we compute the difference of the true reward function at a, and also at a plus some epsilon times Xi. So we move the action a little bit along the direction Xi, and we compute the difference. Then this one gives you a unbiased estimator of the gradient. So with this unbiased estimator, we can just run some gradient ascent, and hopefully it can converge to a local maximum. But the only problem is the sample complexity. So in order to estimate the gradient correctly, we will need at least omega d samples, where d is the dimension of the action space. So intuitively, this is because the gradient is a vector in d-dimensional space, and it has d entries. So we will need d samples. However, for deep reinforcement learning, this sample complexity is not good because we usually have a over-parameterized policy, and the dimension is really high. So if you look at this zero-order optimization approach, the algorithm only cares about the true reward, and it has nothing to do with the model class. But if our model class is very simple, it is quite possible to get a better sample complexity. So our key idea is to leverage the extrapolation power of the model class. In that sense, our algorithm is model-based, and the key technical challenge of our paper is to get a dimension-independent sample complexity. As a starting point of our analysis, we review the typical Ucb algorithm on neural net Bandit. So actually, we show that the model-based Ucb algorithm does not even converge to a local max. So recall that what the Ucb algorithm does is that at time step t, the Ucb algorithm chooses an action at and also an estimated model parameter theta t that maximizes the reward function over every possible action and the model parameter. And we require that the model parameter lies in some confidence region. Okay, so let's see how Ucb works in the construction we gave previously. So recall that in our construction, the reward function is a linear part plus a nonlinear part. And if we take a bunch of actions, like polynomial number of actions, we can only learn the linear part. So the confidence region theta t can pin down theta star, which is the parameter for the linear part, but it has no clue about beta star, which is the parameter or the direction of the nonlinear part. So what the algorithm does is it's like the Ucb algorithm keeps guessing the direction of the nonlinear part. So the figure on the right visualizes one possible reward function computed by the algorithm. So the theta t is correct, but beta t is not. So you can see that the nonlinear part is in a different direction. Because the action is chosen in an optimistic manner. So in this case, the action at will be equal to beta t, which is the direction of the nonlinear part. But the true reward at at actually tells you basically nothing about the true nonlinear part, because beta t is just some random guess. So the Ucb algorithm will not stop guessing unless it tries every possible direction of beta t. But in a high dimensional space, the number of possible directions is exponential. So the Ucb algorithm overexplores, and it doesn't converge in polynomial steps. This is also somewhat true in practice, because deep reinforcement learning method with optimism also overexplore. Okay, so what's wrong with the Ucb algorithm? So in a typical analysis of the Ucb algorithm, we need to show the following two properties. The first one is optimization. It means that the algorithm can achieve a high virtual reward. So for Ucb, this is quite straightforward, because by the optimistic in the face of uncertainty principle, the virtual reward is always greater or equal to the true reward of the optimal action. And the second property is the extrapolation property, which says that the virtual reward converges to the true reward in the long run. So in particular, for Ucb algorithm, the total extrapolation error is going to be bounded by square root of t times some complexity measure of the model class. And this is a typical choice of this complex measure is the Euler dimension. Okay, and you can imagine that with all of these two properties, the true reward of the Ucb algorithm can converge to that of the optimal action. But the problem is for neural net bandit is that the eluded dimension in this case is exponential. So it takes exponential steps for the UCB algorithm to converge. So although the UCB algorithm can achieve a high virtual reward, but the true reward is always much lower. This is also the over exploration. And because the extrapolation of neural net is so hard, so our idea is to reprioritize these two steps. So we want to focus on the extrapolation first, and we want to use a very complex algorithm that especially designed for doing the extrapolation task. And as we know that they are the online learning oracles. So if we use an online learning oracle to predict the virtual reward, we actually guarantees that the expected extrapolation error is bounded by square root t times r of theta, which is a different complexity measure, and also times a polylog factor. And the upper bound of the extrapolation error on the right-hand side is actually actually called the sequential Rademacher complexity. And because the online learning oracle is just designed to do the extrapolation task, so the sequential Rademacher complexity can be much smaller than eluded dimension. In particular,
can I ask a sort of like narrow technical question on this? If
sure.
you, I think that for like linear models or something, you would get something that only depends on log t, not on the square root t. At least in the at least in the statistical settings. Do you think that there's like an extra square root? Do you think in some settings you can just plug in a different bound into your bounds?
Yes, I think it's possible. So I guess if we are just predicting the virtual reward, then it is possible to get a log t for at least a linear setting. But I'll show later that our algorithm, just predicting the reward itself is not enough. We need to predict something else. And with that extra term, I'm not sure whether we can get a log t upper bound even for linear setting.
Okay, so you're saying you're actually going to use one as like a general oracle with different kinds of things plugged in.
Right.
Okay. Thanks.
Okay, cool. So let's go back to the sequential Rademacher complexity. So okay, for finite hypothesis, we can show that the sequential Rademacher complexity R of theta is going to be upper bounded by log size of the model class. And of course, for neural nets, the sequential Rademacher complexity is polynomial in the dimension of the neural net, where the eluded dimension is exponential. Okay, and if we really want to get a dimension-free bound, we can tighten the sequential Rademacher complexity so that it may only depend on the weight norm of the neural network. Okay, and this improvement is mainly because the online learning oracle is doing extrapolation optimally. So recall that the extrapolation error is just the summation of the difference between the virtual reward and the true reward. So we will use the same example to illustrate this idea. And the ground truth reward is just again a linear part plus a nonlinear part. And so what's the prediction of the UCB algorithm? So recall that the algorithm keeps guessing the nonlinear part of the reward. And because the action is chosen in an optimistic manner, so the virtual reward will be the peak of the nonlinear part. But the true reward is just the linear part. So there is a significant gap between the virtual reward and the true reward. It means that the extrapolation error of the UCB is very large. But if we only care about the extrapolation error, there's no point guessing the nonlinear part because the probability mass of the nonlinear part is exponentially small. So anyway, we are not going to see a nonlinear reward. So the online learning algorithm can just output the linear part of the reward, and for most of the times, the extrapolation error of the online learning algorithm will be 0. Okay, so now that we solve the extrapolation problem, we can our first attempt in this direction is to just use our online learning algorithm to predict the virtual reward, and we pick the action, the greedy action, with respect to the virtual reward. Okay, but unfortunately, this simple approach doesn't work. I'll show by a simple one-dimensional example that why it doesn't work. So suppose action is one dimension, and the true reward function is given by this blue curve. Suppose the algorithm takes a bunch of actions denoted by the green dots. One possible output of the online learning algorithm could be this red curve. This red curve predicts the past actions pretty accurate. However, if we just take the greedy action with respect to this red curve, we'll end up taking the same action AT over and over, and we make no progress. So the algorithm is getting stuck at action AT. This is because the prediction is lack of optimism. Okay, but the UCB algorithm doesn't have this issue because it will always pick the optimistic model, but it suffers from the over-exploration. So this is also bad. So this means that it's not enough to just predict the reward function because we cannot guarantee an increasing virtual reward. So in other words, we need the online learner to work harder to guarantee that. This is where we embrace the virtual curvature. So instead of just predicting the virtual reward, we require that the online learner also predicts the gradient as well as a Hessian matrix of the true reward at action AT. So now let me use the same simple example to demonstrate why estimating the curvature helps increasing virtual reward. So recall that this red curve is not good because the algorithm can stuck at action AT. But if we look at the gradient information, we can see that, okay, actually, this red curve is not a good output for the online learner because the online learner does not predict the gradient accurately. So the online learner will know that, okay, this is not a good estimation. So instead, it may output something like this new red curve. And this curve predicts the gradient and the Hessian at action AT accurately. Now, if we take the greedy action with respect to the new curve, actually we can make some progress because we can increase the virtual reward. Okay, so now let me just translate this very simple intuition into equations. So let's assume that the reward function is smooth. And now by the online learning guarantee, the virtual reward is approximately equals to the true reward. And now if we take the Taylor expansion with respect to the previous action AT, we get this inequality. So it says that we can increase the virtual reward if the gradient at previous action is not 0. So this is the so-called descent lemma, or here this is the ascent lemma. And now we can translate this real reward back to we can translate this virtual reward back to the real reward because we have the online learning guarantee. So in this way, we get this is approximately equal to the real reward at action 80 plus some increment in the order of the norm of gradient square. And the first and last equation comes from our learning guarantee. And this derivation tells us that if the action AT is not a critical point of the real reward, we can guarantee that the real reward increases. All right. So with this iteration, we can design the first version of the our while algorithm. So consider the online learning problem with this idealized loss L bar T. And I'll talk about this in a minute, why it's called idealized. But now let's assume that this loss is accessible. So this loss consists of 3 terms. That are the prediction error of the reward function at action AT and action AT minus 1, plus the prediction error of the gradient at action AT minus 1. So with this loss, our while algorithm is just to use the online learning oracle to minimize the loss function, the idealized loss function, and get a distribution of the model parameter theta t. Then we take the greedy action with respect to the virtual reward. So in this way, we can prove that if the online learning for this idealized loss has a sublinear regret, meaning that the online learning loss eventually approaches 0 in the standard sense. So then we have that the action AT output by the algorithm converges to a critical point of the real reward, eta of theta star. And
can I quickly ask a question?
Oh, sure.
So in this L bar T loss, you have 80 and 80 minus 1 for some parts of the loss, it's 80, some of the parts, it's 80 minus 1.
Right.
What's the rationale?
Oh, okay. Yeah. If you look at this derivation, so there are 2 equations where we need the online learning guarantee. The first equation requires that the virtual reward of the upcoming action is close to the real reward, and the last equation requires that the virtual reward of the past action AT is close to the real reward. So the intuition comes from these 2 equations.
And since we paused here, a second question is, I guess on the next slide.
Sure.
So to evaluate this loss, are you imagining some kind of sampling that's not in these 2 steps, or basically, how do you get access to the gradient?
Oh, yes, this
in
is
a bandit problem?
that's where I'm going to talk about in the next slide.
Okay, let's hold the question then. Sorry.
Sure. Yeah, okay. Yeah, that's actually a very good question. So the question is, how do we estimate this gradient error? Okay, so in Bandit, the gradient of the real reward is never observed. this makes sense because if you can observe the gradient, why not just run a gradient ascent, and it solves everything. It converges to a local maximum with a sample complexity that is independent of the dimension. Right. So the way we deal with this term is to replace the gradient error, the difference of the gradient, by the difference of the directional gradient. So like if we take some random projection onto the direction u that is drawn from a unit Gaussian distribution, then we have this equality here. It says that the expected error in the projected gradient is equal to the error in the gradient. And to estimate the directional gradient, or to compute the directional gradient, we can borrow the idea from the zero-order optimization algorithm. We can just compute by a finite difference. So getting back to the previous question, so yes, in the algorithm, we do take multiple actions at each step just to compute this loss. Okay, so the question is how many samples we need to estimate this gradient term accurately. And this is similar to the Johnson-London-Strauss lemma. So in order to preserve the distance of the gradients, the number of samples we need is proportional to some complexity measure of the model class here. However, in contrast, in the zero-order optimization approach, because we are going to estimate the gradient itself, so it requires at least omega d samples to do that. Okay, so finally, we have this final version of the Weyl algorithm. And the loss function is just the idealized loss and replacing the gradient error by the directional gradient error. And the algorithm has 3 steps. At each round, it samples a random direction and compute this online learning loss. And then we use the online learning oracle to minimize this loss and get a distribution of the model parameter. Then we take the gradient action with respect to the virtual reward. And our theorem states that under Lipschitz assumptions on the reward function, the Weyl algorithm converges to an epsilon approximate local maxima in R of theta times epsilon to the -8 steps. Okay, so in this way, we get a dimension-free sample complexity bound to converge to a local maximum.
How come you can estimate the Hessian and gradient in dimension-free here?
Oh, right. That's because we are using the extrapolation power of the model class. So how should I put it? So suppose you only have like 2 possible models, like theta 1 and theta 2. So in order to distinguish those 2 gradients, you only need one
so
sample.
So is nabla eta also low complexity? Like, do you also need the gradient of eta to be low sequential Rademacher?
Right.
I see.
The directional
You're saying so
gradient.
that gradient is also low sequential Rademacher. Okay.
Right. Actually, we have some evidence on that. So suppose we have a finite model class, then the gradient term is also the Rademacher of the gradient term is also going to be bounded by log size. And for a neural network, the gradient of a neural network is also a neural network itself. So So the random marker is kind of similar to the original reward. Okay, so let's go back to the theorem. And this theorem, we have several examples of this theorem. So first of all is the linear bandit with structured model family. Recall that the reward function here is just the inner product of the theta and A. And so when the model class is finite, we will get a sample complexity that is polynomial in the log size of the model class. And also, if we combine this result with the covering number argument, so when the model class contains sparse vectors only, we will get a sample complexity that is polynomial in the sparsity level and logarithmic in the dimension. Because in this case, the reward function is concave, so the local maximum are all global. So we get a global global convergence. We do want to emphasize that our algorithm only our result only hold for deterministic reward, because we rely on the finite difference to estimate the directional gradient. And if we have some stochastic reward, the variance of that estimation is huge, and we cannot get a dimension-free bound. And of course, also there is a lower bound regarding the sparse linear bandit. Okay. And so next example is.
Can I ask, what is the
sure.
action space in?
The action is.
So this sparse thing is only attainable with some assumptions on.
Right.
The
so the action space is like the unit L2 ball in this case.
Okay.
Right.
But then but then actually this is solvable with 2S samples, just by compressed sensing.
Right.
Like.
Right. You are right.
Okay.
Okay. So right. So next example is the neural network bandit, where the reward function is given by a two-layer neural network. In this case, we assume that the norm of the neural network is bounded by some constant. As a result, the sequential random marker complexity is going to be bounded by some logarithmic factor of the dimension of the neural network. And in this case, we get a sample complexity, of course, for local maximum, in the order of like logarithmic to the dimension. And in particular, if the neural network, the instance, has some other properties, such as if the neural network is input concave, then all local maximum are global. So in order to get an input concave neural network, we can basically set the activation to be monotonic and convex, and we set all the weights of the neural net to be negative. Then this neural network is concave in the input. Okay, and given that, we also have some first cut extension to reinforcement learning. So let's compare model-based reinforcement learning with this continuous action bandit. So the dynamics is like the model parameter, and the policy in reinforcement learning is the action in the bandit, and the total return in reinforcement learning is a reward function. Actually, we can observe the total return by rolling out the policy under true dynamics when the dynamics is deterministic. Okay, but there is a caveat here. This is because the total return, the function class of the total return has a very high complexity, because the total return in reinforcement learning is a complicated and maybe recursive composition of the dynamics and the policy. So we don't know how to bound the sequential random marker of the reward, like the total return family, if the dynamics and policies are neural networks. That being said, we still have some result for stochastic policies, and of course with many more Lipschitz conditions. Basically, we proved that the prediction error of the total return, as well as the prediction error of the gradient, can be upper bounded by the prediction error of the dynamics. And in that case, online learning for the dynamics implies predicting the curvature of the total return. So finally, our algorithm is just to run a online learning oracle to predict the dynamics and choose the greedy policy with respect to the output of the online learner. Okay, so finally, as a summary, we prove that a global convergence for nonlinear models is statistically intractable. And we design the YO algorithm that converges to a local maximum with sample complexity that depends only on the model class. And if you are interested, please check out our paper for more details. And thank you for your attention. Any questions?
I think there will be lots of questions, but we have to figure out how to coordinate.
Sure.
Someone want to start us off?
Okay, so maybe I'm going to ask my question about this restriction that you want the rewards to be deterministic for this to achieve any sort of sample complexity. Like, how serious do you think this is, and how important this is for this approach? Because I see this as a bit of a limitation for scaling this approach up to more serious problems. But I'm just wondering, what are your views on this?
Right, that's a good question. So, I think the reason for deterministic reward is to use the finite difference, and I guess this actually we can handle some kind of randomness. So if you like in the same setting of those zero order optimization, like if you can query 2 actions per random instantiations, then you can estimate this directional gradient. And in that case, I think we can also converge to a local maximum. And the sample complexity depends on the variance of that estimator.
Which may depend on the dimensions still.
Right, which may depend on the dimension.
But hopefully not exponentially.
Yeah, maybe not.
I guess already linear dependence would be pretty bad. If you have a neural network which is like over-parameterized, pretty crazy, lots of parameters. I do have a related question. Sorry, just like for continuing Gary's question. So in RL, like, is this deterministic feedback assumption, like, how does it come into the picture, and how, and to what degree does it limit the result?
Okay, how should I put this? So I guess like the start point of the deterministic reward setting is actually the linear bandit. As you know, if we have a linear bandit, even if we have a linear bandit with finite modulus, if the reward is stochastic, it is impossible to get a dimension-free result. Right? Yes. So I guess so. Informally speaking, this it's like you need to somehow depends on the like a signal to noise ratio. For example, if in linear bandit, if you take some random action, the signal will be in the order of like 1 over root d, but the noise is in the order of constant, then there's no way that you can get a dimension-free bound. But if you have a really small noise ratio, sorry, a really small noise, then I guess we can still have a dimension-free bound.
So is it fair to say that what you really depend on is something like the variance of your gradient estimate?
Right. Yes.
Okay, and that just naturally would be dimension dependent if you're estimating it in a bandit way, but maybe not.
So if you have deterministic reward, then it's not.
Got it. But if with additive noise, yeah.
Right. Yes, exactly.
Okay. And I guess in RL, it's a little unclear what the complexity of estimating a policy gradient is.
Right. We don't have a clear picture for RL now.
Yes, for RL, my what was behind my question is really I was thinking about stochastic dynamics, right? If you have stochastic dynamics, then somehow that propagates into stochastic rewards or stochastic returns.
Right.
And so, like, does it mean that the current result is for deterministic dynamics and deterministic rewards, or are you able to overcome this in some way?
Yeah, I guess right. The current algorithm is only for deterministic dynamics and deterministic reward. And I guess it's so with this very straightforward extension, I'm not sure how to overcome the stochastic issue. Like if we have stochastic dynamics, it's quite problematic. But one way to deal with it is to consider a different, stochastic setting. Like if we can query 2 samples or multiple, like constant samples per randomness, we can also estimate the directional gradient and so on and so forth.
Right. So if you have simulation optimization setting, something like that, then you could reset the simulator to some state, try the same action again, do things.
Right.
Maybe you would need to control the random seed in the simulator. Maybe that even, yeah.
Yes, we will need to control the random seed.
That's what you would need, yeah.
So I have another question, which is probably terribly naive, which is, so like, would you consider just using like SGD with these kind of like randomly with these kind of gradient estimators as a viable algorithm for this setting that says, okay, I just forget about estimating theta star, right? I'm just gonna sample gradients in terms of A, if that even makes sense, and then make the gradient updates to AT. I mean, would that converge to a local optima as well?
Yeah, that's a good question.
Like a sample then commit sort of fashion.
Oh, sorry. What happened? Sorry, let me re-share my screen.
But at least you're still here.
Oh, I'm still here? Okay.
Yeah, you are. It just
okay.
You don't
So
see your screen anymore, but
I see.
Okay.
Yeah, let me go back to the
There we go.
gradient estimator part.
Mm-hmm.
Oh, right. So actually, we are not estimating the gradient. We are estimating the distance between the gradient and the true gradient. So I guess I'm not sure what's the right way to incorporate this gradient estimator to S3D. Because if you are running gradient descent, you need to have the full gradient, have the vector instead of there's the distance.
Oh yeah, definitely. No, I'm just wondering that, if you were to do this, right, you just do this sampling business to estimate the gradient and then do SGD with it, and what sort of guarantee would you be getting in the end?
Right. Yeah, then it will converge to a local maximum, right?
And the rate would be comparable to this or no?
Depending on the gradient estimator. So if you have a dimension-free gradient estimator, it is comparable, right?
So I think on that point, one thing I'm sort of struggling with, and maybe I'm not thinking properly, is so it seems from this slide that you're saying, okay, zeroth order optimization would depend on the dimension of the action space, similar to what Gerge is saying. Right, and I guess that, if you have very few, say you only have 2 models that you're considering, it should be easier to generalize across gradients using the fact that there's only 2 possible parameters. So one thing I'm struggling with, though, is if you restrict to actions that are optimal under one of those 2 parameters, then you only have 2 actions. So something seems a little wrong to say that you have a 1,000-dimensional action space that you're considering, that you have to explore when there's only 2 models. Because it's sort of like you're ignoring that some of those actions are not candidates.
I guess so. 2 is not a really good number. Suppose you have 100 model. So it's like the action space is discrete with 100 actions. So in order to try all of them, you need a sample complexity that's proportional to the size of the model class. But here it depends on the log size of the model class.
Yeah, got it. And then basically you do that by managing to get gradient information, which is like
Right, exactly.
So earlier on during the talk, Jean Lee had a question about the somehow around these complexity measures and these sequential Rademacher complexities, and I'm also a little bit confused regarding that. That the sequential Rademacher complexity is basically some more general version of the Littlestone dimension, and that can get pretty huge for rather simple model classes like learning thresholds as infinite Littlestone dimension. So I'm just wondering what assumption that you're making is ruling this out, that the sequential Rademacher complexity is infinite. Or are you just assuming that it's small?
Yeah, I guess it's so at least for threshold, it doesn't satisfy the Lipschitz assumption. So we need the gradient to be bounded. And right. I think in that case, at least for finite number of models, we will always get a log size of the model class.
Yeah, right. That was my guess as well. That the Lipschitz assumption pretty much rules out thresholds.
Right.
That's the case. Yeah. Right. Okay. Okay.
I'll ask another kind of narrow, clarifying question. But so you mentioned something early on about learning the Hessian or something.
Ah, right.
Estimating the Hessian, but then it sort of seems like you're only estimating gradients in what follows.
Yeah,
Is there something here about estimating Hessians?
I think estimating Hessian is much more technical, so I omit that in the talk. So basically, estimate you can also use finite difference to estimate the Hessian. By taking 4 actions, you can estimate the bilinear form of a Hessian. And with that, you can upper bound the Frobenius norm of the Hessian, and then you get a upper bound of the operator norm of the Hessian, and then it should work for the descent lemma.
See, there's a way of controlling the step size.
Right.
Is what you guys are doing. Okay. Okay. But that I guess, again, is a place where you really need no noise.
Right.
So Jason, you started.
I thought the Hessian was to escape saddle points or something.
Right.
Okay.
With gradient we can only converge to a critical point.
Right.
But with Hessian we can converge to a local maximum.
And also for Hessian, can you also do the dimension independent thing? Because it feels like for Hessian you need to find an eigenvector. Which
sorry, what was the last part?
I was wondering for Hessian, is it also dimension independent? Because it feels like you have to find an eigenvector or something like that. Or if you have one negative curvature direction, you need to somehow find it, and you're not going to find it with O of 1 random directions.
Oh, right. Yeah, again, we are only estimating something like the Frobenius norm of the difference of the Hessians. We are not estimating the Hessian itself. We're not estimating the eigenvector of the Hessian itself. We just want to distinguish different Hessians coming from the model class.
I see.
And in that case, we can get a dimension-free result.
I see. Yeah, that makes more sense.
Yeah, I guess now since we are talking about the Hessians, actually regarding the Hessians, it's not we need more technical analysis about that term, because here in order to estimate this distance, so basically we in our assumption we assume that the norm of the gradient is bounded by some constant. So if we take random projections of the gradient, it's also going to be constant. But for Hessians, if we take random projections of the Hessian, it will be something like in the order of the Frobenius norm of the Hessian, which we don't want to assume that is a constant. We only want to assume that the operation norm of the Hessian is a constant. So it need more technical stuff to deal with that.
Yeah. some different direction and questioning. What happens if you have model misspecification?
That's a good question. I think the online learning oracle can handle model misspecification quite well. So yeah, I think like I'm answering this on the fly. So I guess we can handle model misspecification. So if you look at I guess this slide, this lemma. Right. So if we have some misspecification, then the mean theta term inside the expectation, like the model parameter that you're comparing to, is not going to be 0 anymore. So the online learning regret, like the extrapolation error, will never be sublinear in T. But as long as the error is small, I think that will introduce another like term in the sample complexity.
Right. So basically, then that min of theta of the sum of the comparator. So basically, the comparator term in the regret will be something else.
Right.
If you don't have realizability. But is this the only challenge that you have to face?
I'm not sure. I think
because you're also like doing this gradient descent. Well, not gradient descent. Yeah, no. Sorry, but I think that things can go wrong a little bit in other ways. I'm not fully convinced that it's easy to handle the specification here.
Yeah, I'm not sure. Maybe I'll need to double check offline.
Yeah, it is difficult for me to think of what can go wrong here because I'm not quite familiar enough yet with this algorithm. But but I'm almost sure that something can go very wrong here if there's misspecification.
Okay. Any particular reason for that?
No. It's just the usual skepticism.
Experience that something always goes wrong. Bandits and misspecification don't work very well.
Yeah, that I agree.
So, looking again at this loss, so kind of it feels to me like the spirit of what you want to do is say, okay, I mean, from your initial motivation, it's like I have a policy class that's very rich, but I have a simple model class that I'm going to fit to the dynamics. But, sort of an unfortunate thing in practice would be that to actually minimize this loss over the model class, you'd need to have access to the policy gradient of I don't know, the policy gradient for every policy parameter, and to minimize that over somehow the models
Right. I agree. Yeah.
Do you think there's a way in which this kind of could generalize to doing like maximum likelihood? Is it really essential that this is the loss that you are today?
You mean to learn the model?
Yes.
Yeah, I'm not sure what happens if we use likelihood. I guess it will require a completely different analysis, I guess.
Related question, maybe. Is my feeling correct that like the whole thing is mostly geared toward the case when you have finitely many different models. So for example, this online learner, like how would you even implement it if you have some continuous space or whatnot? Like, I guess it's gonna be computationally intractable for most of the cases that we care about. Like, let's just take neural networks or whatnot, right? As something simple.
Right, you're right. So I guess theoretically speaking, I'm not aware of any computationally efficient algorithm for online learning on neural network. But I guess if you really want to implement this, you can try something like for the perturb leader.
Yeah. Maybe some other local, I don't know, optimization things are coming in. It's kind of interesting that like we had a problem with global optimization, we switched to local, but in the process we're introducing this other potentially nonlinear, like difficult optimization problem where you kind of have the same issue anyways. So once we decided about some local stuff, like one would think that like at least we should have some computationally efficient solution, because that's
I guess it's
local optimization.
I think it traded statistical for computational difficulty. Like the online learning oracle is only computationally hard. Like you lowered your statistical guarantee, but not the computational.
Right.
What you need computationally somehow.
Right.
Right, exactly.
So one thing about your talk that I really appreciate is these pictures at the beginning of what makes bandit optimization with neural networks hard. I mean, I think that's probably not sufficiently appreciated.
Thanks.
But when I've thought about things like this, I don't know what the right response is. Like, is the right response? Maybe this is a better like closed session question, but is the right response to locally maximize? I mean, you could say, okay, neural networks are good because everyone uses neural networks to classify images, and that we like local optimization because that seems to work. I guess I don't know when I see pictures like that whether the right response is to use neural networks and locally optimize, or to say that if you want to do decision making, you need to impose an inductive bias that's stronger than that the function is a neural network, right? Because neural network could be anything. So,
right.
Why did you settle on sort of a local optimization rather than saying that neural networks are not a reasonable thing to try to optimize?
I guess the answer is in practice, people do use neural networks, and it works fine, right? For all those tasks. So I guess that's why we want to try neural network.
So yeah, that's maybe true. But if it works fine, do we need new algorithms, or we just need to understand why they work fine? I guess like the algorithms that people would use, right? Like are much simpler than what you presented today. And does this point to that like there is something missing still in the setup and like in a way of thinking about these problems?
Right.
But generality, like I'm all for that. Don't get me wrong, but
yeah, good question. I guess at least here, one message is that for neural network you cannot use optimism, and I guess that's that's empirically also true.
Is it?
No.
I get mixed messages from whoever I'm talking to. I didn't develop this very strong feeling that people would have given up on optimism. It's time to time revisited. Some group comes along and then demonstrates strong empirical results that have some sort of optimism. Of course, there's a lot of other things also going on, usually in this empirical work, so you never know. But yeah, I don't have the impression that optimism was decided to be a bad choice, but maybe it is.
Yeah, actually, this is, I guess Tengyu told me this, like his previous paper, like the Shelve paper, when they try, in that paper they use a lower bound optimization, and I think he told me that they tried upper bound optimization, like the optimism, and it's just the same phenomenon here. It's like your model is just going to give you a Disneyland, but it's not true. Once your policy decided to go there, you will find that okay, it's just some random place. Yeah, I guess. Yeah, I'm not aware of more, empirical study on this.
I think that some of the ways people inject optimism puts a little more constraint on it's somehow imposing a little more of a bias. Like okay, one example of a thing people can do is like some kind of ensemble method where they tweak the data, kind of add noise to the data, train a whole bunch of different neural networks on slightly different data, and then so basically you're bootstrapping, and you could say which of this ensemble generates the best. So best model in the ensemble, best action for that model. Do this joint optimization. There's somehow, if there's something that means that if there's some bias, like implicit bias in SGD training a neural network, that means that these all converge to the same low-dimensional family of models, you're leveraging that, right? So.
Right.
I wonder if there's an implicit bias that is not just that it's a neural network, but that there's a parameter set for that neural network that's the real model.
Yeah, it's like when you're doing this ensembling and randomizing your data, most of the proofs look at that like you're optimistic with a constant probability, but what if not? Like with a constant probability, you're not. And in these nonlinear settings, you're learning even on those cases, and you're collecting rewarding even in those cases. So maybe there is the underdog of these ensembling methods. It comes back on the back door, and it actually improves performance in some unexpected manner. Although it's hard to see how this could be a systematic advantage as opposed to a coincidental. It's not very clear to me that you can actually play this out and then claim that this is like a good property of these models, that they're not optimistic all the time. But I would want to say as well that like you can somehow tune how much optimism you're injecting in various ways. But there is some conflict, right? Because in the nice and clean kind of convex-ish settings, you want optimism, and in the other settings, maybe you don't want that much optimism, and it's not very nice when we have to make these choices.
Right, I agree.
Yeah, so I mean, I think that in some ways, I guess if you look at your pictures, they're about a phenomenon that's broader than optimism. They actually say that it's kind of impossible to take your data and then build reasonable prediction intervals. Right, for also two different tasks. Yes. Yeah, for causal inference, and so it says that if you're going to do prediction intervals, which are pretty useful to people, then you need to impose something about the neural network. Maybe Jason knows more about that.
Yeah, it's not rigid, basically. I mean, I think, yeah, like, I think it's basically when can you get prediction intervals? It's exactly when you can recover parameters and get L infinity error. That's basically the only instance you can get a prediction interval, or not like a, yeah.
And so again, are people trying to restrict the parameter set in some ways to allow this, or?
I think in deep learning, no, they still just, I think those prediction intervals, at best, you can kind of think that they're good only near the training distribution. Like they're like on the data distribution, they're probably fine. Like, yeah. But yeah, but not to extrapolate. Yeah, I would guess. But none of them, they look like each they're Bayesian methods or some sort of resampling. Yeah.
Okay.
Yeah, like the needle thing looks like just, there's no way to extrapolate that. It's not rigid enough, the model. Your model, curves in a sharp way. Yeah, like, I mean, a polynomial cannot do that, basically. Like, but as soon as you don't have a polynomial, like a seat, like, yeah, even an analytic function cannot do that, but it could get kind of close-ish, I think.
So Kwang, you had a question in there. I don't know if Chava's comment addressed that. Maybe you want to unmute yourself and ask, Kwang?
Yeah. Just a quick comment. It seems like your work is basically a pure exploration. So in that case, you usually, optimism is not like necessary. Like you can use optimism to show some guarantee, but you don't have to. And there are elimination strategies, and in general, like pure exploration problems, like optimism strategies, I don't know if they work well. Yeah, it's yeah, that's all I wanted to say.
All right, that's a good point. Yeah, we do have some like regret guarantee in our paper, but I'm not showing in this talk because it's kind of a little more complicated than this. Right, and I totally agree with the pure exploration part. Yes, but right, as Saba says, like even for pure exploration in neural network, it's still hard.
Yeah, I agree. It's hard.
Right.
It's just that, it's, I don't know if people actually use it, but yeah, for pure exploration, I don't think optimism is a good idea. I just don't have like evidence that it is a good idea. Like if you consider simpler problems, yeah, for K-arm bandit, there's an algorithm that uses UCB. You can guarantee sort of minimax, no, not minimax, but you can guarantee a good bound, but it doesn't work well in practice. There's other algorithm that works better, but yeah, that's all I got.
Yeah, I agree. I agree.
For some reason, though, all of the usual setup in RL is to solve a pure exploration problem, but everyone treats it as if it was an online problem. So this seems to be not just you, I guess.